In mathematics, the mean value theorem states, roughly, that given the planar arc between two endpoints, there is at least one point at which the tangent to the arc is parallel to the secant through its endpoints. The theorem is used to prove global statements about a function on an interval starting from local hypotheses about derivatives at points of the interval. More precisely, if a function f is continuous on the closed interval a, b, where a less than b, and differentiable on the open interval, then there exists a point C in such that a special case of this theorem was first described by Parameshvara from the Kerala School of Astronomy and Mathematics in India, in his commentaries on Govindaswamy and Bhaskara II. The mean value theorem in its modern form was later stated by Augustin Louis Cauchy. It is one of the most important results in differential calculus, as well as one of the most important theorems in mathematical analysis, and is useful in proving the fundamental theorem of calculus. The mean value theorem follows from the more specific statement of Rolle's theorem, and can be used to prove the more general statement of Taylor's theorem. Formal statement. Let f, a, b, r be a continuous function on the closed interval a, b, and differentiable on the open interval where a less than b. Then there exists some C in such that the mean value theorem is a generalization of Rolle's theorem, which assumes f equals f, so that the right-hand side above is 0. The mean value theorem is still valid in a slightly more general setting. One only needs to assume that f, a, b, r is continuous on a, b, and that for every x in the limit exists as a finite number or equals plus infinity or minus infinity. If finite, that limit equals f. An example where this version of the theorem applies is given by the real-valued cube root function mapping x to by 1/3, whose derivative tends to infinity at the origin. Note that the theorem, as stated, is false if a differentiable function is complex-valued instead of real-valued. For example, define f equals EIX for all real x. Then f minus f equals 0 while f 0 for any real x. Proof. The expression minus f gives the slope of the line joining the points, and, which is a chord of the graph of f, while f gives the slope of the tangent to the curve at the point. Thus the mean value theorem says that given any chord of a smooth curve, we can find a point lying between the endpoints of the chord such that the tangent at that point is parallel to the chord. The following proof illustrates this idea. Define G equals f minus Rx, where R is a constant. Since f is continuous on a, b, and differentiable on, the same is true for g. We now want to choose R so that g satisfies the conditions of Rolle's theorem, namely by Rolle's theorem. Since g is differentiable and g equals g, there is some C in for which g equals 0. And it follows from the equality g equals f minus Rx that, as required, a simple application. Assume that f is a continuous, real-valued function, defined on an arbitrary interval I of the real line. If the derivative of f at every interior point of the interval I exists and is 0, then f is constant. Proof. Assume the derivative of f at every interior point of the interval I exists and is 0. Let be an arbitrary open interval in I. By the mean value theorem, there exists a point C in such that this implies that f equals f. Thus, f is constant on the interior of I and thus is constant on I by continuity. Remarks. Only continuity of f, not differentiability, is needed at the endpoints of the interval I. No hypothesis of continuity needs to be stated if I is an open interval, since the existence of a derivative at a point implies the continuity at this point. The differentiability of f can be relaxed to one-sided differentiability, a proof given in the article on semi-differentiability. Cauchy's mean value theorem. Cauchy's mean value theorem, also known as the extended mean value theorem, is a generalization of the mean value theorem. It states, If functions f and g are both continuous on the closed interval a, b, and differentiable on the open interval, then there exists some c, such that, of course, if g and if g 0, this is equivalent to. Geometrically, this means that there is some tangent to the graph of the curve which is parallel to the line defined by the points g and g. However, Cauchy's theorem does not claim the existence of such a tangent in all cases where g and g are distinct points, since it might be satisfied only for some value c with f equals g equals 0. In other words, a value for which the mentioned curve is stationary. In such points, no tangent to the curve is likely to be defined at all. An example of this situation is the curve given by which on the interval -1, 1 goes from the point 2, yet never has a horizontal tangent. However, it has a stationary point at t equals 0. Cauchy's mean value theorem can be used to prove L'Hopital's rule. The mean value theorem is the special case of Cauchy's mean value theorem when g equals t. Proof of Cauchy's mean value theorem. The proof of Cauchy's mean value theorem is based on the same idea as the proof of the mean value theorem. Suppose that g. Define h equals f minus rg, where r is fixed in such a way that h equals h, namely, since f and g are continuous on a, b, and differentiable on, the same is true for h. All in all, h satisfies the conditions of Rolle's theorem. Consequently, there is some c and for which h equals 0. From the equality h equals f minus rg it follows that, as required, if instead g equals g, then, applying Rolle's theorem to g, it follows that there exists c in for which g equals 0. Using this choice of c, Cauchy's mean value theorem holds. Generalization for determinants. Assume that, and are differentiable functions on that are continuous on. Define there exists such that. Notice that and if we place, we get Cauchy's mean value theorem. If we place and we get Lagrange's mean value theorem. The proof of the generalization is quite simple. Each of n are determinants with two identical rows, hence, the Rolle theorem implies that there exists such that mean value theorem in several variables. The mean value theorem generalizes to real functions of multiple variables. The trick is to use parametrization to create a real function of one variable, and then apply the one-variable theorem. Let G be an open connected subset of Rn, and let f, gr be a differentiable function. Fix points x, y, g such that the interval x, y lies in G, and define G equals fx plus I. Since G is a differentiable function in one variable, the mean value theorem gives for some c between 0 and 1. But since g equals f and g equals f, computing g explicitly we have, where denotes a gradient and a dot product. Note that this is an exact analog of the theorem in one variable. By the Schwarz inequality, the equation gives the estimate. In particular, when the partial derivatives of f are bounded, f is Lipschitz continuous. Note that f is not assumed to be continuously differentiable nor continuous on the closure of G. However, in the above, we use the chain rule, so the existence of f would not be sufficient. As an application of the above, we prove that f is constant if G is open and connected and every partial derivative of f is 0. Pick some point x 0 g, and let g equals f minus f. We want to show g equals 0 for every xg. For that, let E equals xg, g equals 0. Then E is closed and non-empty. It is open to, for every xe, for every y in some neighborhood of x. Since G is connected, we conclude E equals G. Remark that all arguments in the above are made in a coordinate-free manner, hence, they actually generalize to the case when G is a subset of a Banach space. Mean value theorem for vector-valued functions. There is no exact analog of the mean value theorem for vector-valued functions. Jean Dieudonné, in his classic treatise Foundations of Modern Analysis, discards the mean value theorem and replaces it by mean inequality, as the proof is not constructive and by no way one can find the mean value. In applications, one only needs mean inequality. Serge-Lang in Analysis I uses the mean value theorem, in integral form, as an instant reflex, but this use requires the continuity of the derivative. If one uses the Henstock-Kurzweil integral, one can have the mean value theorem in integral form without the additional assumption that derivative should be continuous, as every derivative is Henstock-Kurzweil integrable. The problem is, roughly speaking, the following. If f room is a differentiable function and if x plus th x hrn t 0, 1 is the line segment in question, then one can apply the above parametrization procedure to each of the component functions phi of f. In doing so, one finds points x plus th on the line segment satisfying, but generally there will not be a single point x plus t asterisk h on the line segment satisfying for all I simultaneously. Equals cos f2 equals sin, then f minus f equals 0 r2, but and never simultaneously 0, as x ranges over 0 to pi. However, a certain type of generalization of the mean value theorem to vector-valued functions is obtained as follows. Let f be a continuously differentiable real-valued function defined on an open interval I, and let x as well as x plus h be points of I. The mean value theorem in one variable tells us that there exists some t asterisk between 0 and 1 such that, on the other hand, we have, by the fundamental theorem of calculus followed by a change of variables, thus, the value f at the particular point t asterisk has been replaced by the mean value. This last version can be generalized to vector-valued functions. Let urn be open, f room continuously differentiable, and xu hrn vectors such that the whole line segment x plus th 0 t1 remains in U. Then we have, where the integral of a matrix is to be understood component-wise. From this one can further deduce that if df is bounded for t between 0 and 1 by some constant m, then proof of right phi for the real-valued components of f. Define the functions g 0, 1, r by g equals phi. Then we have the claim follows, since df is the matrix consisting of the components q, e, d. Proof of. From it follows that here we have used the following lemma. Let v a b room be a continuous function defined on the interval a b r. Then we have proof of. Let u in room denote the value of the integral now that is desired. This shows and thereby finishes the proof of mean value theorems for definite integrals. First mean value theorem for definite integrals. Let f a, b, r be a continuous function. Then there exists c in such that since the mean value of f on a, b is defined as, we can interpret the conclusion as f achieves its mean value at some c in general, if f a, b, r is continuous and g is an integrable function that does not change sign on a, b, then there exists c in such that proof of the first mean value theorem for definite integrals. Suppose f a, b, r is continuous and g is a non-negative integrable function on a, b. By the extreme value theorem, there exists m and m such that for each x in a, b, since g is non-negative, now let if we're done since means so for any c in, if I is 0, then by the intermediate value theorem, f attains every value of the interval m. So for some c in a, b, that is, finally, if g is negative on a, b, then and we still get the same result as above. QED second mean value theorem for definite integrals. There are various slightly different theorems called the second mean value theorem for definite integrals. A commonly found version is as follows. If G, A, B, R is a positive monotonically decreasing function and phi, A, B, R is an integrable function, then there exists a number x in function and phi, A, B, R is an integrable function. Then there exists a number x in such that mean-value theorem for integration fails for vector-valued functions if the function returns a multidimensional vector. Then the MVT for integration is not true, even if the domain of is also multidimensional. For example, consider the following two-dimensional function defined on a dimensional cube, such that, then, by symmetry it is easy to see that the mean value of over its domain is. However, there is no point in which, because everywhere, a probabilistic analog of the mean value theorem, let x and y be non-negative random variables such that x less than y less than infinity and then there exists an absolutely continuous non-negative random variable z having probability density function. Let g be a measurable indifferentiable function such that g less than infinity, and let its derivative g be measurable and Riemann integrable on the interval x, y for all yx0. Then, g is finite and generalization in complex analysis. As noted above, the theorem does not hold for differentiable complex-valued functions. Instead, the generalization of the theorem is stated such. Let f omega c be a holomorphic function on the open convex set omega, and let a and b be distinct points in omega. Then there exist points u, v on lab such that where re is the imaginary part of a complex-valued function,